Can I just write like a C program that uses all of these procedures? So coroutine go, it definitely doesn't return anything, but it accepts the pointer to the function. It's a pointer to the function that also doesn't take anything. Init, this one doesn't return anything and doesn't accept anything. Yield is kind of similar if you think about it. So and now we should be able to create something interesting like counter int 0 10 plus plus I. So maybe here we can include stdio io print f d. And here is the entry point for routine init, coroutine go, just use counter, let's create like 2 of them, and indefinitely, let's just yield like this. And by the way, we should also yield on each iteration of the counter too, otherwise it's not going to work properly. I guess that's it. Holy shit! Let's fucking go! Let's fucking go! Look at that! I have coroutines in C, motherfucker! Implemented in assembly, in a completely fucking different assembly, not even a GNU assembly. Fuck GNU assembly, FASM. FASM is the way to go. Alright, chat. Do you guys know what the fuck is coroutine? I should probably not start the video with a what the fuck. Otherwise I'm gonna get demonetized. I mean, I'm not monetized in the first place. So fuck that. Do you know what the fuck is a coroutine? Right. So essentially, let's actually take a look at some example. A very interesting example. We're gonna write that in C because it's an example. I want to be able to actually quickly start an example. So imagine you have a counter, right? So and it's a simple procedure that just counts shit. Right, so you do something like from 0 to 10 plus plus I, and you probably just want to print f, something like d I. So it's basically counting from 0 to 10 and printing the numbers it is counting. So you run that in the main procedure, right? So let's actually compile the entire thing, main.c, and run the entire application. Okay, so, but then I want to actually run the same routine, the same procedure, but in parallel. Right, so I run it in parallel and, well, I mean, yeah, I'm running it sequentially. So if I do it like that, it's not going to be in parallel, right? So first, the first call executes, then the second call executes. But I want them to be interleaved. So essentially, I could probably run them on separate threads, but how exactly they're going to be interleaved is particularly not particularly predictable. So essentially, coroutines allow you to implement that. So they usually, traditionally, introduce like a special keyword like yield, right? So, and there's different kind of coroutines that work in a different way, have different kind of properties and different kind of keywords. So I'm looking like it's very basic, very generic coroutines, right? So imagine you have a procedure and it's executing in a loop, and on each iteration after printing this thing it calls yield. Right. So, and essentially here we can use maybe a Go notation, and we can say that run that in a separate sort of coroutine, right? So this is how usually Go does that. Right, and what essentially will happen is that this routine executes, it prints I, then on yield, it will switch its context, it will switch its execution to the next routine, execute the code until the next yield, and then switch to the next one and next one. So it's basically going to round... All right, we're back. So yeah, this one actually was quick, right? So today we only started, we already went down, so I had to, turn off the VPN and stuff like that. So I'm glad that we're back. Right, so essentially, we are running 2 coroutines, and they're running sort of like simultaneously, right? And every time you call yield, it switches the execution to the next coroutine, where the next coroutine actually called yield. Right, so this yield becomes sort of like a switching point between several coroutines. And what's interesting is that all of that can execute on a single thread. So we're sort of switching the execution context within a single thread without any multi-threading or anything like that. So why would you need this kind of stuff? For the same reason, you would need futures, right? So remember, we developed like a future library for C3, right? So, and the whole point is kind of to be able to do something while you're waiting for something else. Like in case of asynchronous networking, right? So in case of asynchronous networking, you have non-blocking sockets that may have something to read or they have an opportunity to write, but maybe sometimes they're not ready to read or write. And while they are not ready, you don't want to waste time, you don't want to waste CPU cycles, you want to do something else. And this is where futures are really useful, right? So because they basically split the code into these small blocking chunks, and between those blocking chunks you can actually do something else, right? The same thing in here, so it could be used for the same purpose, right? So essentially you're doing something within a coroutine, and then you encounter something that like you have to wait for something. Okay, so I can basically tell the runtime, the execution engine, okay, go do something else. I have nothing else to do right now, so go do something else, and you yield. Right. You can even say that, okay, so don't resume me until that socket, has something to read or something to write. You can even do something like that. It's sort of like the same purpose. In fact, futures are literally kind of like that, aren't they? So we can take some of the examples, right? So I think here we have a very simple example without any highlighting or anything like that. And here we even have a counter. Right, so an counter future. So let's actually maybe fetch the stuff from the future library, right? So it feels, when I looked at how coroutines worked in the libmil library that we looked at, on one of the previous stream, right? So on one of the previous stream, and we looked into this library, and this is, by the way, what inspired today's stream, right? So I looked at this library and I got really inspired, and I wanted to explore how exactly you even implement things like that. Libmil, yeah, exactly. So here's the libmil. I'm going to go into the description. So here is the libmil, and let me see. So let's actually find the stream where we did. I can't find the stream because it turned out the VPN, so I don't have an access to YouTube. I'm sorry. So I'm gonna do something like a libmil stream, right? To be done. So it's going to be in the description for the YouTube people, but you here in Twitch you can just Google it up, right? So I think it's one of the like latest videos. I think it's called something like "This library turns C into Go" or whatever. Right. So essentially, I get really inspired, and it feels like futures and coroutines are kind of isomorphic. They're kind of like, yeah, they're kind of the same, right? So essentially, the future has poll, right? So if you take a look at the interface of the future, here it is. So interface future, right? So it's just an object that has a method poll that gives you a result telling you that something finished or not. And the execution environment, the runner of the future, is supposed to constantly poll it, constantly call this thing, checking whether the job is done or not. And so the future itself is supposed to do a little bit of work within that poll, and then return status pending, telling the executor, telling the runner that, okay, go do something else. And you may have several futures, right? And the runner is going to just like poll one future, right? Look at the result of this future and then poll another one and another one and another one. So essentially, it's a mechanism to tell the environment, I'm done for now, go do something else. Kind of similar to what the coroutines are doing in here, right? It's kind of similar to that, right? So here I'm just like saying, okay, go do something else. Go do something else. I really liked this approach because it's a little bit more readable in the sense that it's easier to reason about, because it feels like just, a sequential imperative code. When you're working with futures, if you take a look at the examples, they look horrible, honestly. They kind of look horrible. So here it is. So here's how you do the counter, right? Look at that. So you're supposed to implement poll, right? And within the poll, you extract the state, you check that the state is less than 10, you print that state, and then if it's less than 10, it's pending. If it's not, it's finished. So this is how it looks like. This is one single feature. Whereas with coroutines, you basically do just a regular loop and you just insert additional yield in here, right? So it's better, it looks better, it feels better, it's easier to reason about. But the question is, how the fuck do you even implement that, right? So like how do I stop execution, especially in C and C, like, or in C3, right? How do I stop execution and switch to a completely different context? Like, how the fuck do I do that? So in fact, if the language doesn't have an explicit support for this kind of stuff, there's nothing much you can do anyway, unless you go lower level, right? Unless you go lower level, there's nothing much you can do about that, because it's a mechanism that has to be implemented explicitly on a lower level. With futures, you can kind of implement them on a higher level, right? So if you don't have an explicit support for coroutines in your language, like, you don't need anything special. You can just implement this abhorrent, you know, interface, and it kind of works. It kind of does what you want, but it's kind of meh, right? So, but maybe functional programming fans love this kind of interface, right? So because future feels like kind of a monad, even though some functional programming purists will say, no, it's actually not a monad because it doesn't satisfy monadic laws that nobody fucking knows about, only I know about, because so I can feel elitist and stuff like that. So, you know, right, so maybe people like that kind of love futures. But as you can see, they're kind of difficult to work with. So I as an imperative programmer, right, so who actually gets the shit done, unlike functional programmers, I would like to, you know, think imperatively. I would like to think imperatively. So, and I want to explore how you would even implement something like that. How you would implement something like that. So first of all, you kind of have to save the execution, the context of the execution. And this kind of vaguely reminds me long jumps. Do you guys know what are long jumps? So there is a regular go-tos and stuff like that that allows you to jump over things. Right, so for instance, you can say, you should never see me, right? So you should never see me, and then you go to skip, right? So, and then here you have a label skip, and then you can put something like hello in here, right? So you can put something like hello in here, and then we can try to compile this entire thing. As you can see, I never actually seen this printf because I literally skipped it. Right, so you can jump around however you want, right? So Dijkstra said that go-tos are bad, and because of that, every time programmers see go-to, they have a seizure. So I suppose like half of the audience right now is literally having epilepsy, right? So I really apologize for that. So I know that Dijkstra said that it is bad, but we are trying to explore things in here. So stay open-minded. We're gonna do a lot of horrible shit today. Seriously, just be prepared. That's kind of welcome to the Tsoding channel, by the way, right? So where we say fuck establishment, fuck best practices, we do whatever the fuck we want because it's a recreational programming, motherfucker. It's a recreational programming, motherfucker. We just enjoy what we do. Fuck you. So that's basically the Tsoding channel. Anyway, so you can jump around, but unfortunately, you can't jump to a different procedure, right? So I can't really create a label inside of this thing. Honestly, it would be actually kind of cool, and it would like basically do what we expect. I can't jump into foo, right? So if I do something like jump into foo, it will, yeah, label foo used but not defined, right? So it's not defined. So we can only jump within the procedure, but you can't really jump between the procedure. And this is where long jump comes into place, right? So we can take a look at this. What is long jump? Long GMP. Yeah, perform a non-local go-to. Perform a non-local go-to, and it consists of two functions. It consists of two functions: set jump, which accepts environment, and long jump, which also accepts environment and a value that set jump will return. So essentially, set jump acts like setting a label. Right, so it acts like setting a label. So what we can do in here, essentially, imagine that we have along a call stack, right? So essentially in here, we're calling foo, right? And so within foo, we're going to be calling bar, like so. We're calling bar, and within bar, maybe we're going to be printing something, right? So we can say bar. Maybe within foo we can also print foo, so we can have some sort of like tracing in here, right? So we have some sort of a tracing, and essentially, what I wanna do, I want to basically put a label somewhere here, right? So let's say jump buffer, right? So this is the environment, and then I say send jump environment. So essentially, this call takes the current execution environment, takes the entirety of the execution environment, and saves it into this opaque variable. We don't really know the type of this variable. It's absolutely opaque. In fact, it's architecture specific, right? So it's even platform specific. Like it depends on the current CPU you're running and also the current operating system. And libc usually implements like all of the possible combinations, right, and stuff like that. Well, I mean, libc usually works on POSIX operating system, right? So, but it usually basically has like a little snippet of assembly code for each individual architecture. In fact, we can even see that, right? So you can go into something like Musel, which is a very simple, lightweight implementation of libc. So we can put it somewhere here. So it's going to be in the chat, and for people who's watching, is going to be in the description. And also, I think I want to put my futures library into description as well, right? So here it is. So let's actually download. I think I already have it downloaded. I do in fact think that we have it downloaded. So here is Musel. You can literally just search for a file with the name set jump, right? So do that already. Okay, so here it is. And the extension S is assembly. And look at that. Here are all of the architectures, all of the different CPU architectures. And for each individual CPU architecture, it has a little assembly snippet, right? So we can even take a look at x86-64, right? So, and this is how it is implemented. So set jump is literally just a sequence of, x86-64 instructions, right? So it's never implemented in C. You can't even implement it in C, right? You can't implement this thing in C because C is too high level for this kind of thing. We need to go like lower level, right? And what it does, look at that. So RDI is a register that contains the first argument. So it's basically sort of like a pointer. And look, it actually basically treats it as an array of 64-bit integers, and it saves different registers in here. Right, so it basically just saves registers into this buffer. So you have some sort of a buffer and it dumps registers into that buffer. So then later you can restore it. So essentially what it does, it saves the current execution environment. Right. So, and then what we can do, right, so we save this environment in here, and I think we can make it global because I want to be able to access this variable from within bar, right? So, and in here, what I do, I perform long jump, right? So, and what this thing will do from here, it will jump back into set jump through all of the call stacks. Look at that. Through all of the call stacks, it will jump back to here. Right, but in that case, it will actually call foo again, so we're gonna go into this infinite weird loop. And this is why long jump actually accepts a parameter, right? So if you just do set jump as it is, it returns 0, false. But then if you do long jump with 1, this particular call will return 1 or whatever you put in there. And that way you can actually distinguish whether you just setting a label for the first time or you jumping or you restoring the environment. Right, restoring the environment. So essentially in here, if not, so basically it returns 0. So we do call, otherwise, jumped back, jumped back. Now, if we try to run this entire thing, it's going to be rather interesting. So jump is not available, so we have to actually include something. So it is probably available in one of the headers. Set jump, please. What's the header? Oh, it's literally set jump.h. Okay, fair enough, fair enough. Okay, so, and we kind of forgot to add new lines for each individual thing in here, so let's quickly do that. Okay, so there we go. So look at that. It said foo, but it never said bar, it then jumped back. Look at that. So, and jump back is behind this else. So we went into foo, then it printed foo, we went into bar, and then it jumped back, skipping bar, and since it jumped back to here and returned 1, which is true, it then went here. Look how non-linear it is. Right, look how non-linear it is. You can basically save the current execution environment and then restore it. And that feels like exactly what we, like this is mechanism through which you can kind of implement coroutines, can't you? Like here it is, like right there. So yeah, so because you save an execution environment, so and then at some point in the coroutine you can say, okay, switch to the next execution environment. You can have an array of these things. Right, you can have an array of these things and you can just basically switch between them and stuff like that and it's gonna be fucking cool, but no! Fuck you! You can't fucking do that! Who knows why? Who knows why you can't fucking do that? Scapt exception. Yeah, it's kind of like scapt exceptions. How to follow how code executed. I mean, we're talking about coroutines. Call stack size. Yeah, so essentially this is because of the stack. At least I think so. Right, so, and there is even a note about that. I think it's in this section, undefined behavior. Yeah. If the function which called setJump returns before long jump is called, the behavior is undefined. Some kind of subtle or unsettled chaos is sure to result. Here is the thing. The state of the execution is not only the registers, it's also your current stack, right? So this entire thing, if we take a look at the implementation of this function, the only thing it does, it just saves the stack pointer. Nasal demons incoming, yeah. Right, so it just saves the stack pointer, but the stack still stays the same. The stack stays the same. And if you have several coroutines, what essentially is going to happen, they're going to share the same stack, and they're going to be overwriting their own state on the stack constantly between each other, and some sort of a chaos will, you know, ensue. Some sort of a case will ensue. We can even like maybe, you know, draw that. I think it will be kind of useful. I think it's gonna be kind of useful. So do I have my thingy majingy? Hopefully. So here is the stack. I'm not sure how can I conveniently place myself in here, but so here's where the stack begins, right? So this is a stack pointer. And very importantly, the stack grows towards 0 address. It doesn't grow towards plus infinity, right? So it grows towards 0. So every time you call a function, a return address after the call of the function is put on the stack so you can return back. So this is what primarily the stack is used for. Then the procedure that you called, puts some sort of arguments in there or local variables, right? So you can put vars in here, like this. Then it may call another function which will result in return address put again, and so on and so forth. As you execute the code, the stack grows and shrinks all the time. It grows and shrinks all the time. So essentially, imagine that at this specific point where you're executing, and then you say yield to the next procedure, okay, we jump to the next procedure, but the stack, for example, for that procedure was pointing here as well. So that stack is like, that procedure is going to have the variables of the previous coroutine. So if you have two coroutines on the same level, they're going to be overriding its own local variables. That is why you have to do set environment, set jump in here, and always do long jump when you're somewhere here. Right. So you have to do long jump after you did set jump, not after like you returned it. Right? Because otherwise you grow in the stack and some sort of a garbage on the stack is happening. Right. So this is quite important. Because of that, you can't really use set jump and long jump for implementing coroutines. To implement coroutines, you have to literally have a copy of the stack for each individual coroutine. Right, and as you switch the coroutine context, you have to literally switch the stacks. That's what you have to do, otherwise it's not going to work. Can you have multiple stacks for each core? This is a cool idea. Where did you get that idea from? So thank you. We'll think about that. So, just right now, cool. So yeah, essentially, not only we can't use existing language mechanisms, we can't even use the standard library, even though the standard library kind of has something resembling what we want, but we can't use that, right? So because it doesn't clone the stack, we kind of need to clone the stack, right? And that means like we have to dive really, really balls deep into assembly, as much deep as possible. And that's what we're going to be doing today, on today's stream. Sounds good? Sounds Gucci? Sounds what? Tamaguchi. Let's fucking go. Let's actually do assembly, finally. So I want to do everything entirely in assembly, right? So the coroutines are going to be implemented in assembly. We're going to implement the counter also in assembly. I want to do everything in assembly to minimize the amount of noise introduced by the compiler. We could have used inline assembler in C compiler or in C3 compiler. By the way, C3 has an inline assembly, which is actually kind of cool. I haven't tried it yet, but maybe in the future we're going to try it. I can't open it because C3 is banned in Russia for dangerous propaganda. So yeah, so C3 is actually spreading very dangerous propaganda in Russia, which is threatening the state. So anyway, but trust me, it has inline assembly, right? It does in fact have inline assembly. So, and because the compilers may generate all sorts of shit, right? So in preamble and like, you know, prologue and epilogue of the function, right? Prologue and epilogue is usual names for boilerplates that, you know, compilers put between the begin and end of the procedure. They can introduce some additional noise and stuff like that. I want to minimize the amount of noise, right? So we have full control over what is going on, so we can understand precisely what the fuck is going on in a very low level. I think it is important, right? I think it is in fact important. So let's create a simple, you know, ASM program, right? So we already did a stream where I sort of refreshed my assembly skills, right? So you can maybe watch that stream on the YouTube. I can't open YouTube, but I'm going to put myself a TBD, right? So TBD stands for the big D. So it stands for to be done, all right? So assembly stream, right? So I'm going to put that there when I upload the video. So let's do format ELF64 executable, right? So executable, and let's just create this kind of thing. So we need to do as, you know, exit syscall. So I'm going to move into rex sys exit, and I just happen to remember that sys exit is actually 60. The reason why I remember it is because we literally did it on the previous stream, so I still kind of remember these codes. Right, so to program an assembly, you don't have to remember any of that shit. You can always look it up, right? So you can do like a Linux, you know, syscall table. syscall table. I already did that. So in here it is, you can just look it up there. I just happen to remember that it's 60 because I worked. It's also banned in Russia. Okay, is the Chromium also banned in Russia? No, Chromium is not banned in Russia. Okay, that's cool. Okay. So we can do exit, and in this specific case, it's 60, right? So as you can see, I was right. I remember that. Okay, so an RDI, which is the first argument, is going to be the exit code, sys69, and let's do a syscall. So let me rebuild the whole thing. So this is going to be something like that. Let's fucking go. And now if I try to run that, it does in fact return 69, which is pretty cool. Okay, so let's create some sort of a message. Right, so let's say maybe hello world, new line 0. And then here, let's put something like a message len, which is the current address minus the address of message, which effectively gives you the length. So, and then here, we can do rex syswrite, and I don't remember what is syswrite. It's either 0 or 1. It's actually 1. 0 is read. Right. So, and here RDI is the file descriptor, stdin file no, right, which is also 1. I happen to remember that. RDI, so RSI is the buffer message, and message len, and then we perform syscall message len. All right, so let's actually try to run that, and we have an illegal instruction at 19, which I do not quite understand. So because this has to be db to allocate some bytes, you have to do db, and it exited abnormally, but it didn't print anything, which is kind of weird in my opinion. So because I supposed to put RDX in here. Okay, so, and it also printed 0 in here. Oh yeah, I forgot. Yeah, we're supposed to put 0 like everywhere in here. By the way, I haven't acknowledged the subs, people have been subscribing, so let me quickly do that. So thank you so much, the rugged bear, for tier 1 subscription with the message Coroutines. Very funny indeed. Numeral 0, thank you so much for telling me the message. Listen to the stream makes me realize my assembly couldn't handle Zosin's coroutines. I mean, it's all about the practice. There's also Google, there's also ChatGPT. You can learn all that stuff. AliMark71, thank you so much for Twitch Prime with the message. New to Twitch, shy. Do I have to manually resubscribe every month? I don't really know, because I don't really subscribe to anyone else. I can't do that. But as far as I know, Twitch Prime, I think Twitch Prime has to be manually resubbed, right? So it's just the regular subs that are automatic, but Twitch Prime is manual. So Raz Junior 08, thank you so much for Twitch Prime with the message. Thank you, Mr. Zosin, for kickstarting my interest in recreation programming again. You're welcome. That's exactly my goal. Tam Voodoo, thank you so much for Twitch Prime, and Johnny DeResta, thank you so much for Twitch Prime with the message. What's syscall a 69? Let's actually find out. 69. A message sent. It's sending the message. Message sent. That's what it is. I have no idea what the fuck is that. Message sent. So message queue operation. So yeah, that's what it is. That's what it is. Are you satisfied, my friend? Are you satisfied? I hope you are. Anyways, so let's actually do 0 in here, and so on and so forth. So anyway, we need to be able to, you know, print numbers, right? So from the previous stream, I got a routine. So I got a routine which allowed me to print numbers, which I implemented a long time ago in Porth. So I'm going to copy paste it in here, right? So this is a routine that accepts a number through RDI, the usual call convention on Linux, and it just prints that number on the standard output plus new line. The way I implemented this entire thing, I implemented this entire thing in C, and I compiled it down to assembly using C compile, and then I copy pasted it in here. So people ask me, how do you program an assembly? I don't. I just program in normal language, and I just compile down to assembly and just copy paste. Whatever works. Like, I just don't want to implement it. I could implement this thing manually. Like, I know how to do that, right? So the basic idea is that you allocate a little bit of a space on the stack, right? And then you divide the number by 10 and mod the number by 10, filling the digits into this stack, and then you use that stack space as the buffer for the write syscall. So that's what this entire procedure does. It was just like easier to describe it in C, right? So, and as you can see, it also optimized it a little bit, right? So it uses really weird optimizations with these huge negative numbers and stuff. And by the way, here it allocated some space on the stack by subtracting RSP and stuff like that. So yeah, it did a good job. C compiler did a good job. So that's why nobody programs in assembly anymore, by the way, because C compilers are sufficient for this kind of shit. Anyways, so we can actually test how it works. So let's put move RDI 69 and call print. So that should do it. And it didn't fucking work. And it's quoted. I think it's not RDI, RSI? Is that what it is? Bro, what the fuck? It's scuffed. Yeah, it's supposed to be RDI and it didn't work. What the fuck? Huh. No, it doesn't work. I'm surprised. Like, I forgot that you need to put entry in here. So it basically, if you didn't specify the entry, it just starts the execution from the top. Right, and at the top we have print, and we didn't have anything there. So what we have to do, we have to say entry, and as you can see, it prints 69. There we go. There you go. There you go. You can actually put whatever numbers in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever fits into your register, and it actually prints all of that very conveniently. So we can't really use printf because we don't really link with the standard library. Right. So, okay, let's actually implement the counter routine. Let's implement procedure that we're going to be using as a coroutine. Right. So let's do counter. And in here, we need to have a counter. Right. So let's actually allocate that counter on the stack. Right. So let's allocate that on the stack. So I wonder how we're going to be doing all that. So maybe I'm going to save the previous stack base, right, on a stack. And then I'm going to say that the current stack is the new stack base. Right, so RBP or stack base is basically, like, as you can see, as I already said, the stack is constantly growing, right, to the left and right, it's constantly growing. But sometimes you want to have like a stable address within the stack, right, that doesn't move constantly left and right, like relative to which you can identify the variables. So quite often after, you know, after you call the function, you have a return address, right? So what people do, they save on the stack the previous RBP value, right? So which was probably used by the previous function, right? And then they set the current RBP value to this. So that means it doesn't matter where the RSP moving left and right, you always have the stable value relative to which you can identify the variables and stuff like that. Right, so yeah, that's basically what's going on here. And in here we can maybe even say like subtract RSP8. So essentially we allocated 1 byte on the stack, right? So we allocated 1 byte on the stack. And when we are returning out of the function, we kind of need to do the opposite operation. So we add 8 bytes to the RSP, basically deallocating the variable. Then we are popping RBP, and then we are returning. So essentially, people really take it for granted. People really take it for granted when they basically define variables, local variables within procedure and stuff like that. They never have to manage them, but if you're programming an assembly, you have to allocate local variables and deallocate them automatically, right? So here I'm allocating a local variable manually, and then at the end of the function, I'm deallocating it. So, and essentially, what I'm going to be doing, so the variable is going to be located at the address RBP minus 8, right? So it's located at RBP minus 8. And the first thing I want to do probably with this variable is actually set it to 0, right? So it's going to be 0. So then we're going to have a start of the loop somewhere here. So the first thing we do at the beginning of the loop, we check in whether the current variable exceeds a certain value, right? So for example, we can compare it to 10. Right, and if it is greater or equal than 10, we want to kind of, you know, finish the entire loop, right? We're going to do over, right? So we're going to have a special label in here. So if something like this happens, it's over. it's Jover. Okay, so, and in here, what we're gonna do, I'm gonna take the current sort of like pointer, right, and I'm gonna move it into RDI as an argument for the print, and I'm gonna call print, right, so I'm gonna just print the current counter. After that, I'm going to simply increment this specific variable, RBP minus 8, just incrementing it, and just doing it again, right, so just do it again, I'm gonna do it again, and we're gonna be doing it again at comparison, right? So here is the basic loop, right, which allocates a local variable, which is basically like I variable, initialize it with 0 and just like iterates and prints the variable until it becomes 10, and then it just exits. So that's basically the entire procedure. Very simple one, nothing particularly special. So let's actually try to maybe call this procedure once, call counter, like so, and it doesn't work. Operand side, oh yeah. So essentially, here I'm trying to set 0 to the address located at RBP with an offset minus 8. But I didn't say how many bytes I want to actually write there. So I have an address, I say write 0 at that address, but I mean, what is that? Is that a byte? Is that a short? Is that an integer? Is that a, you know, long integer? What is that? Right, so, and in fact, since I allocated 8, it's basically 64-bit integer. So that means it's a quad word, right, in terms of assembly, right? So I'm saying that save quad word in here. So, and it probably will complain in here as well, right? So let's actually see. Yeah, in fact, it complained in here as well. But it's not going to complain in here, by the way. It's not going to complain in here. Right, so now it complains at increment, it also complains at increment, but it's never going to complain in here. Right, so, and the reason is, you're trying to move this thing into the 64-bit register. It infers the size of the read from that address from the size of the register into which you're saving. So depending on what kind of size of the register you use, it will just read different amount of bytes in here. So you never really have to specify how much you want to do the read and write there. But if it can't infer that, you have to explicitly say that, right? So that's basically how it works, right? Hopefully that makes sense. But anyway, so if I try to now run the whole thing, right, it actually prints from 0 to 9, as you can see. So it just prints from 0 to 9. Type inference in my assembly, yeah, exactly. So, and this is basically the counter routine that we implemented. And I suppose one of the things I want to be able to do in here is I want to be able to call coroutine yield or something, right? So some sort of a procedure, and that procedure should switch to the next, you know, counter routine, right? Somehow, by modifying the stacks, by modifying the environment and stuff like that, it has to do that. Luckily, we are programming in assembly, so we can actually do all of that stuff. So I'm going to comment it out for now. Right, so if I just call this entire thing, right, so as you can see, it just like executed one, then it executed another, and so on and so forth. So this is not going to work that easily. Okay, so first we need to be able to allocate separate stacks for each individual coroutine. So that's one thing we need to do. Let's actually go ahead and just allocate, like at the end of the executable in here, let's just reserve like a huge ass buffer, right? Huge ass buffer, and say that this is where we're gonna have all of the stacks, right? So there's gonna be stacks, and just like reserve bytes, like, and allocate like, I don't know, 100, 500, like a lot of bytes in there, and there we go. So I don't want to be calling to malloc or anything like that. Just like allocate shit ton of stuff. So to be fair, what we can do, we can basically say that we can limit the amount of coroutines you can actually start within a single application, just for the demonstration purposes, for the exploration purposes. Right, so we can say coroutines max, or maybe capacity, right? So capacity. And let's say that you're going to have 10 coroutines, right? So we're going to have arrays of stacks and maybe arrays of arrays of contexts, and we're going to have, you know, their size to be this thing, right? So that way we don't have to work with dynamic memory too much. So, and let's actually say that we're also going to have like a stack capacity, right? So the maximum capacity of the stack per coroutine. So what's the ideal capacity for the stack? Is 1 kilobyte for the stack enough for everybody? Look at this thing. How about 4 kilobytes? So yeah, I don't know. So 4 kilobytes is okay. So let's actually put 4 kilobytes in there. So essentially here we can allocate, you know, coroutines capacity multiplied by the stack capacity. Stack capacity. There we go. So this is how we're going to be doing all that. So Golang has 1 kilobyte. Oh, people know how Golang in general works. I personally don't know. So yeah, thank you for telling me. Right. What's interesting is that we can now build it, and the size of the entire executable is actually this. What's funny is that if you move the reserve before the message, the size of the executable will blow up to 41 kilobytes. Right, if you put it in here, it actually becomes 310 bytes. So this is because RB doesn't really set a specific value, it reserves a certain amount of memory. So I feel like you have to do the reserves at the end of the executable, so then the assembly has an opportunity to just like not actually include any zeros in there or anything like that. But if you say reserve in here, fuck, what the fuck is going on? Okay, but if you say reserve in here, and then a specific value, I think it will literally just fill everything with zeros and then put hello world at the end. We can actually check that. I think I want to see that. So let me actually open. It didn't, bro. Where is main? Oh, I'm sorry. I just like sorted it. Okay, so here are the zeros. You know, at thingy with the cap. Is basically 0. This is how Emacs denotes 0. Then at the end, yeah, and at the end we have a hello world. So it's he, so here's he, and here is a low world, right? So maybe I can, yeah, here it is. So it literally put hello world at the end, and then it reserved a shit ton of zeros. So that's how it works. So because of that, when you reserve things, you have to be really careful. So it's better to reserve this kind of things and initialize memory at the end, right? So that way, you're not creating huge ass executables. So as you can see here, it's just like 310. So I suppose when you reserve everything at the end, it gives the opportunity for the compiler to just create an elf that can be just mapped to memory. And then you can say, okay, after that specific point, just like uninitialized or filled with zeros or whatever. And the operating system will just do that so you don't have to store that additional information. So this is how I presume it works. Anyways, so we also need to store, on top of like having a space for the stack, we need to have our own jump buffer environment, right? So our own environment things. So to be fair, since we're programming in assembly, we're not really modifying registers too much. Like we don't really care if we retain the states of the registers, right? So the only registers that are important for us to retain here, I suppose, are RSP, the pointer to the stack, RBP, the base of the stack or the base of the frame, and REAP, right? So basically current instruction pointer. So we only care about RSP, RBP, and the instruction pointer. So we can only save those. You know what I'm talking about, right? So for now, since it's sort of like a exploration, let's not overcomplicate everything. Let's not just save everything as, for example, set jump does in Musel, right? So it saves shit ton of different like registers and stuff like that. Let's not do that. Let's not do that. Let's only save these things. And I think for now, these things are the only things we care about. So where can we actually store all of that stuff? So it would be nice to maybe store them in a structure, right? Some sort of a structure. Right, so let me see. So xbps query f FASM. Here is the documentation. Let me grab the documentation. You didn't copy paste it in the right place, bravo. Okay. So struct. I really don't like the structure syntax in FASM. It doesn't really make much sense to me. I still have not figured out how to make arrays of structures. Right. So it allows you to create a bunch of things, but how do I create several of them? I have no idea. I literally have no idea. Like, so, okay, we can go ahead and maybe just, you know, create this kind of thing. So when we can say this is the context, right? And within the context, we're going to store the current RSP, which is going to be, you know, reserve queue, right? So it's just one 64-bit integer. So then RBP RQ1 and then RP also RQ1. So this is the register that we are storing in here. So, and obviously then what I want to do context C, and I just want to allocate a bunch of them, right? So, but I can only allocate one in here, right? So it's going to be one. But how do I do several of them, right? So it doesn't make any sense to me, right? So it compiles, but can I do repeat? So there was a rept. So what if I want to allocate coroutines capacity? Is that something I could do? So let me see, FASM, like this. Yeah, so you're telling me that I can just do something like this. Do I have to put curly braces in here? Yeah, you can't do that. That's illegal instruction, and you can't even repeat that several times. It's so bizarre. All right, so it has a mechanism for creating structures, but it doesn't have a mechanism of creating arrays of structures. Like, I could never understand that. Does anybody know how to create arrays of structures in FOSM? It's just so bizarre to me. And the official documentation doesn't have anything about arrays or several of them. There's a times keyword, like I just tried rept keyword. Are you talking about rept keywords? Right, so I tried it, it doesn't work with structures. There's no times. Right, so there's no times directive repeats one instruction number of times. Blocks of instruction, okay. So can I, okay, times repeat this one. No, none of that works. None of that actually works. So it's bizarre because it's kind of useless. If you can't create arrays of structures, the entire thing is useless. The entire thing is entirely useless. So if we can't create arrays of structures, can we create structure of arrays? Wait. So because one of the things, wait. You can parameterize this motherfucker, right? So that means I can put, yeah, I can actually just put something like coroutines capacity. Yeah, how about fuck you? Yeah, so I think, like, I just don't know. Repeat, people are just, guys, if you don't know for sure, there's no need to confabulate different things, right? Like, I can confabulate myself different ideas, so like times, repeat, while, loop, like, I can confabulate that myself. I don't need chat for that. If you don't know for sure... Anyways, right, so we're gonna have a structure of arrays. We're gonna have a structure of arrays. So, and I suppose now we should be able to do contexts RSP, right? So, and then we can access it with, like, by offsetting it, right? So by offsetting it in a certain way. Right, we'll see how it goes. So let me see if it compiles. It does in fact compile. So I suppose now, what we need to do, we need to have a structure, we have an operation that creates a new routine. Right, so let's create coroutine go. Right, and I suppose the easiest thing in here would be for this procedure to actually accept the pointer to the function that it needs to execute to start the routine. Right, so let's say RSI, the procedure to start in a new coroutine. Right, so that's what we're going to be doing here. All right, so here's the procedure. So, and I suppose how we're going to be approaching this entire stuff. So I'm going to move into RSI the count, the counter, and then I call coroutine go. Right. So, and I can call that like several times. So, and it should create several coroutines. Okay, that's cool. The first thing, we need to check the capacity, right? We need to check the capacity of this entire thing. So we need to track how many contexts we already allocated, right? So that means we need to have something like contexts count, right? So, and this is going to be RQ1, right? So this is a single 64-bit integer, not cout, but count, right? And in here, so what do? We take this value, and we compare it to the coroutines capacity, right? So the maximum amount of coroutines we can have in here. And since we can't really infer the size of the read in here, we have to say it's a keyword. Okay. And if that value is greater or equal to the coroutines capacity, we should probably just fail the whole execution, because this is sort of an assertion, right? This is sort of an assertion. So let's actually do overflow fail, right? So this is an overflow fail. And in that overflow fail, we can just straight up like exit, right? So with non-zero exit code and whatnot, like with 69. Right, and we also want to probably print the message that like too many coroutines, right? So move rex sys right, move RDI, too many coroutines message, but I mean it has to be something like an std error file number. This one is RSI. This one has to be RDI. Assembly is hard. RSI, RDI. All right, and this one RDX. Right, and this one is going to be length. So, and then we do syscall. So we just need to allocate the message for too many coroutines, right? So let's actually put it like somewhere along with other messages like hello world. We probably don't even need hello world anymore, right? So fuck that. Too many coroutines. Don't forget the 0 and then the new line, right? So then we're going to put a length in here, and it's going to be just that. There we go. We don't need hello world, and here is the message. Here is the message. Yep. So in here, maybe I'm going to put something like int3. So int3 basically creates a debug interrupt for those who doesn't know, right? So it's a special debug interrupt, and so usually that interrupt invokes the debugger in one way or another. So if you don't have an operating system, I suppose you just create a special routine in the interrupt table, the famous interrupt routine, right? So how many of you actually read an interrupt routine in the chat? Tell me. So yeah, so for this kind of thing, you're supposed to write an interrupt routine, I suppose, which calls to a debugger or something. Right, and so when we are in an operating system, I suppose GDB can actually handle that, right? So if you run in a GDB and you throw this sort of like interrupt, GDB will stop at that specific place, right? So I'm going to use that as sort of like an indication that this thing is not implemented yet. I love seeing embedded. We have embedded developers in here. Mr. Terry would be proud. I think I wrote an interrupt routine once when I was developing pinpog. So pinpog. So for those who doesn't know, it's just a simple game that works without operating system, right? And it fits into 512 bytes of the bootloader, right? So, and obviously when you're working on that level, you kind of have to write interrupt routines, right? At least for the timer and also for handling input. I don't remember. I think input was also a specific interrupt. But specifically for timer, I actually had to write some stuff in here. So I'm going to put that in the description for anyone who's interested. It was fun. It was fun. So I can proudly say that I did, in fact, wrote an interrupt routine. So I don't really write them very often, but like at one time I actually wrote it. But I mean, it's literally a callback. I'm not even joking. It's literally a callback, but on a very low level. So, isn't it? Look, embedded developers, please confirm. This is just a literal callback. Right, you put an address into that table, and the CPU will just call that procedure there. But when something happens, callback, literally callback. If you, oh, I also did that in Unix stall, not Unix. How do you sell it? UXN, right? So this little thing. So it's a small virtual machine, very small virtual machine, and yeah, it's based on interrupts, right? So it has a lot of events that may happen within the virtual machine, the timers, the inputs, and stuff like that, and all of that is interrupts. You really have to like create special interrupt routines and just like register them and whatnot. So it's also pretty cool. So I wrote that. So okay, good. Okay. So Yesu. So I'm gonna put in3 in here. I want to kind of test if this thing is going to fail. So yeah, if I try to run this thing right now, it is going to fail with the sig trap thingy, right? So let's actually go ahead and try to do that. So it's going to be sig trap. STD error no is not available. Okay, so this is the actually this is 0 out. Did I confuse std in with std out again, chat? I think I did. So we don't. Yeah, we only. Yeah, I think I did confuse them again. But anyway, as you can see, it's like yeah. So it's basically trap thingy. So it will basically stop the debugger at that specific place, but we don't run in the debugger. So yeah, it's fine. UXN not banned in Russia. Yeah. So which is pretty cool. I really appreciate that. So and now we can try to maybe set coroutines capacity to 0. No cock routines are allowed. Cock blocked routines. Okay. Too many coroutines. Perfect. And it actually exited with 69. So that specific assertion works correctly. That specific assertion works correctly, and if you have enough routines, it actually allocates them and then goes into in3 thingy in here. Okay, we confirm that. We confirm that that specific part of this thing, it actually works. I really like that. So what's cool is that we don't even have to return from this routine, right? Because we call exit, so it's just like we can fire and forget, right? Just fire and forget. Okay, cool. So here is an interesting thing. RSI is the address into which we have to jump. So what we need to do, we need to take the current index of the current routine. So the context count contains basically right now the index of the newly allocated context, right? So we have to allocate the new context at that specific place. So let me read the value stored in that address into some sort of a register, like which one, like maybe rax, whatever, right? So let's put it into rax, maybe rbx, because rax is used for syscalls. So I don't know, maybe I'm gonna actually clubber it. Do you guys know what is clubbering or whatever? So it's just like when you like trash the registers, right? So because register is in a constant flow state, right? So anyway, so the rbx stores the index of the context that we care about, right? So, and essentially what we can do, the context starts at that address, right? So this is the label that we have in here. So they do start at that address, but we only care about RSP part of that context thingy, right? RSP part. So we could have actually, do we even need structures in here, chat? Do we even need that? Like, I mean, I can just do something like, I feel like we don't need structures. Like, if we're going to be doing like a structure of arrays, who said we can't do something like this? And we can maybe prefix this like context RSPs or BPs and yeah. Fuck that. SOA, AOS, you know, structure of arrays, array of structures. So we're optimizing our our replication earlier, right? So data-oriented stuff, you know, so data-oriented programming. Be careful about cache locality gatekeepers. Yeah, I mean, it's like we're just prototyping anyway, so we're picking whatever solution is easier to implement. So as of right now, this is easier to implement, so we're going to be going with that. Maybe I'm going to even take like remove this thing, right? So remove s. I'm removing s, so it makes it a little bit easier for me to read. Okay, so here's the index, and I want to assign the stack, right? I want to assign this stack in here. What's funny is that the stack grows from positive values to negative. So that means we have to allocate the stacks in here from right to left. That makes sense, I suppose. I think that in fact makes sense. Right, so essentially here we have like stack. Let's put it like this. So it's going to be like this. And we have a bunch of sort of reserved spaces for the stacks. So if we allocate the new stack for the routine, we have to say that the stack starts in here, right? So it starts in here. And so as the routine goes and does things, it's going to be allocating memory into here. And if the stack overflows, it will start overriding the stack of another coroutine. We can try to prevent that by maybe putting some sort of stuff in here, but I mean, let's just like, don't do stupid things, right? If you're afraid of doing stupid things, go program in Rust, right? So Rust is the language for you here. We live dangerously. We're programming in low-level assembly. I mean, the reason why I don't care right now is because this is a prototype, right? So obviously in the future, it would be kind of nice to maybe put some sort of like a thing in here that triggers something when you actually try to read right there. I don't really know how to do that, but that would be nice. Right, maybe separate it with pages, like each individual stack. Imagine separated with pages with like 0 permissions where you can't really read, write, or execute. So every time the stack overflows, yeah, it goes into this area, it actually segfaults. That would be nice, right? So don't really allow them to overwrite. But again, right now, I don't want to overcomplicate it. That would be nice. Put impenetrable wall. Yeah, that would be nice. So because of that, like, we have to allocate them from the end. So because as we allocated this stack, when we create a new coroutine, we have to allocate this stack in here. So we have to jump through these stacks. So because of that, I feel like it's kind of difficult to use context count to keep track of all of that. Maybe we can have another variable, which is something like stacks and, right, and so this is going to be a pointer, and it's a pointer that is going to be pointing at the end of these stacks. Yeah, we can do something like that, but we need to initialize it with something. Right, so we need to initialize with something. I wonder if I can... If I could do something like db, I could have just said, okay, it has... Yeah, that would be actually perfect. If I manage to do something like this, look at that. But then all of that stuff is going to blow up the size of the executable. Right. This is going to blow up the size of the executable. So maybe I can put something like this. So this is the stacks, but plus the size of the whole thing in here. Is that something we can do? Right, so that will point at the end in here. Huh. So let me try to compile this entire thing just to see if it's going to work. So value out, okay. Okay, so you can't do that. It's out of range, like you can't literally assign it like that. Damn, Brevsky, damn. Okay, so can I just do, oh, it's not, yeah. Ah, it has to be DQ. Maybe I still can do that. Yeah, maybe I still can do that. Okay, you know what I want to try? In the main, okay, so this one is going to be int3, and I'm going to load up into racks stacks and then into rbx stacks end. But since it's a variable, I have to read it. So this is just a static address that points at the buffer that stores all of the stacks and stuff like that. And this is the variable that is going to be changing. Right, so, and I just want to load them up into the registers and see that the difference between them is exactly the size that I expect, right? So just to see that it initialized everything correctly. So if I try to build this entire thing, the size of the executable didn't blow up. We're still below 1 kilobyte. It's not like it's goal or anything, but I mean, I don't want it to blow up too much. So, and then we can just do gf2. Right, so let's fucking go. So here we are loading the address of the stacks, right? So it is in racks now. Sorry. Okay, so in here it is. So I wonder if I can, I can't even copy paste, bro. Can I? Okay, I can probably print this stuff in racks and then I can print rbx. Can I copy paste them now? 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 Okay. So, and if we take a look at this kind of stuff, so the size is 10 multiplied by this. We can do 10, 1 kilobyte, and 4. Yeah, it's initialized correctly. T2 SDE, thank you so much for the raid. Thank you. Hello, Raiders. Hello. How was your stream? So we're just programming in assembly. We're not doing anything super cool and advanced or even useful, I would say. We're just exploring how to implement coroutines on a very low level. Right, so in assembly, right? So we're kind of like learning assembly, so to speak. We're kind of like learning assembly. Okay, so this is actually very useful. That's very cool, I would even say. Okay, so here is the index. And essentially when I create a coroutine, I suppose what I can do, I can literally just set the RSP of that new routine to the stack's end. I can just set it there. Like, who said I can't do that? Like, yeah. So that's your new RSP. So I take the stack end, that's your new RSP, and then I subtract the stack capacity from stack's end. So then on the next coroutine allocation, I can again use stack's end as the RSP for the new coroutine. So it'd be nice to use stdin to specify a coroutine number. Yeah, so we're definitely going to be keeping track of the current coroutine, and this is going to be a variable. So yeah, so as we switch between things, we're going to be incrementing this variable and wrapping it around. And who said this variable can't be used within the coroutine? Each coroutine can just look at this global variable and know what coroutine it is. So, and use that in the output just to see like what is going on in there. So that sounds pretty cool, I think. That sounds pretty cool. So I'm going to allocate it with that. Look at that beautiful alignment. Isn't it perfect? I think it's pretty perfect. Okay, now might as well, by the way. Yo, perfect. So we still keep all of the reserves in here. All right, so, and kind of related variables are near to each other. Really like that. So stack's end is modified. Yeah, stack's end is modified. So it's basically like an allocator. So it points at the end of the stacks buffer. We use it as the stack for the new coroutine, and then we subtract it. So then we can use the next chunk for the next coroutine, then subtract again the next chunk. So it's a simple allocator. So it's a simple like slab allocator. How is it called? Right, so it's a, but it allocates actually in the opposite direction. Usually slab goes from left to right, but since it's a stack, we're going from right to left because it makes sense for the stack. So yeah, it's kind of cool. Listen, chat, I just got the fucking, yeah, it's a bump allocator. Yeah, thank you so much. What if coroutine go as it allocates the stack? As the last element on the stack, it pushes the address of some sort of a routine which deallocates the coroutine. Holy shit, this is such a cool idea. So yeah, so this coroutine will eventually return, and it may return into the address that we, as we were allocating the coroutine, put in there, and that routine will deallocate everything. That is so fucking holy shit. I really like that. Okay, but let's not jump ahead of ourselves. So I already streamed for 1 hour. I think the time has come to make a small break, chat. Right, so because I ran out of tea, I want to refill my cup of tea, and then we're gonna continue. So I think, yeah, I think it's doable. That's so cool, right? So it doesn't. You don't even have to call explicitly anything to deallocate the routine, right? So we can just put the return address there. It's like a defer. Yeah, it's kind of similar to defer. So the time has come. The time has come. Right, so make some break and up. All right, let's continue. So yeah, so we don't need these shites anymore. It was just a debug shites, and we are implementing the coq routine. All right, so here is the stacks and so on and so forth. So I suppose we might as well just increment context count, right? So let's actually keep RBX as the index of already allocated context, right? So that's totally fine. So and after that, I'm instantly incrementing it, right? So yeah, so I'm just incrementing it as it is. So then it can be reused for the next coroutine goal. So and in here, RBX is an index. We need to find the location of the RSP because we want to set up the RSP thingy. So that means it starts somewhere here, right? So here is the RSP plus an index, but it also has to be multiplied by the size of the element of this array. The size of the element of this array is actually 8 because it's a quad word, 64 bits. So that means it has to be multiplied by 8. So this is the address into which we have to save the stack ends, right? So essentially we have to move stacks end into here, right? And I don't know if it's going to work. I think you can't move one memory into another memory. Like I don't quite remember, at least in x86-64. We can try to build the whole thing. Come on, you can do that. Yeah, invalid operand. We can try to maybe save that value into rex. So yeah, let me actually put some notes in here. RBX contains the index of the current context, right? Of the context we just allocated. Can I? Oh, I can even wrap around. Thank you, Emacs. Very cool. So rex contains the RSP of the new routine. Yeah, there we go. So this is rex, and I suppose it is going to work. Invalid opera. I forgot to. Oh, okay. So do you tell me that I can actually move this kind of stuff in here? But can I say then keyword? Can you specify? Yeah, you have to first save that thing into a register and only then. Okay. So that's understandable. So this is RSP, and we're doing this stuff like that. What's interesting is that here is kind of a deceiving thing about Intel style assembly. It makes it feel like you can put arbitrary arithmetic expressions in here. Actually, it's not true. you can't put arbitrary. You can't like put minus racks in here. Right, you literally can't do that. It's an invalid address. So you can only put, basically you have very specific roles for each individual element in here. So you have the base address, then you have an index address, and then you have like sort of like a scalar or multiplier. So, and this is, you can only have these three things and that's it. It's like a Leah instruction, yeah. You can only have these three things. And they are part of the format of binary format of the instructions. The binary format of the instruction literally has 3 places for this specific formula, right? So the thing that goes before plus or minus, right? So then the, you know, the index and the multiplier. And yeah, so I don't like AT&T syntax, but in that regard, AT&T syntax is at least more honest about what the fuck is going on underneath. You know what I'm talking about? In AT&T syntax, you can't really do this kind of stuff, right? So it literally, you have to put this thing in specific places, right? It actually reveals what's going on underneath the syntax, right? So we can even take a look at that, AT&T syntax. But I personally like Intel syntax more because I actually started programming on Windows, right? So, and I also started to learn assembly on Windows. And on Windows, everything is Intel syntax. AT&T syntax is usually a POSIX things. So I have like a more of a sentimental value towards Intel syntax, right? So it's kind of weird. Even though there are some parts of AT&T syntax that are just like objectively better. Like for example, the syntax for these kind of operations. Intel syntax objectively superior. Yeah, I kind of like it, right? So it's, I mean, syntax by the creators of the processor itself, right? So it kind of makes sense. Versus Intel. So is there some sort of comparison? Intel or AT&T limitations of the Intel syntax. Can't really find. Is there some formula? Memory operand, complex mnemonic suffixes, data size declarations. Yeah, essentially, right. So the syntax is the following. Instead of writing EBX plus 3, they would write 3 in parentheses ABX. And then the index and multiplier would go into their separate places. So instead of writing this, they would write something like, so this is an offset. I don't remember, something like this probably. I don't remember even. But yeah, so they would put these kind of things in like different places and whatnot, right? So is that what it is? Right, I think that's what it is. So somebody actually provided an example. Yeah, thank you. Like I'm not particularly familiar with the syntax, right? So add this becomes, yeah. So you literally just specify them in their corresponding places. So it doesn't lie to you, right? So this one makes it feel like you can put whatever stuff in here. In fact, you cannot, right? So and here it just like you explicitly specify different roles for things, right? You specify roles, right? Thank you so much. You have no idea what AT&T syntax does, though. At least plus and well, yeah, true. Sometimes you look at AT&T, you kind of have to know that, but here you look at it and you instantly see what it does, even if you don't know that there's like different roles for different places in here, right? So, yeah. It's basically like tabs versus spaces at this point. Okay, so here we're saving RSP. So what's going to be the initial RBP? What's the initial RBP of the main program, right? Because RBP is usually set up by the procedure, but we're only starting the procedure, right? So it's sort of like an entry point. So let's actually stop in here and let me just try to do GF2. All right, so I'm gonna run it. And what's this value of RBP, initial value as we started the program? Oh, it's actually 0. Okay, so, all right, let's set it to 0 then. So this one is gonna be RBP and it's gonna be 0. So, and next thing is we need to have instruction pointer, REAP. So what's going to be REAP? REAP has to be the RSI, or is it RSI? So what's the call convention? The first thing is RDI, actually. This one is RDI. And when I call to this one, we already set it to RDI. So the current execution point has to be the whatever we have in RDI. All right, so we basically saved everything in here. we basically saved everything. But I suppose another thing we have to do in here is subtract stack end with the size of the stack, right? So we have to do something like sub, right, stack capacity, right? So then it can be reused for the next thing imaging. So, and after that, I suppose we just return. So essentially, as you create a new coroutine, it does not start the coroutine immediately. It's going to wait for the next yield, right? It's going to wait for the next yield. Yeah. So it just registers that coroutine in the table of like in the contexts, right? And doesn't execute it. So it will only start executing on the next sort of yield when you actually switch to that coroutine. So let me actually try to run the whole thing, right? So here we just create two coroutines. And what we expect in here is that this thing will just like exit successfully, right? So let's actually go ahead and try to run that. Right, so it doesn't like something about 79. I actually have to subtract the value in here, right? So I'm subtracting it as keyword, obviously. Yeah, operand size not specified. All right, for the 0, right? So here it can infer this kind of stuff from the register, but here it can't really do that. So let's actually set 0. Okay, so I didn't really want to run the debugger, I just wanted to run this thing. Okay, so it exited with success. So let's maybe create an OK message of some sort so we can test things. So this is going to be OK. So sys write. So let's write into std out something like awk mate. So it has to be actually not capitalized. Let's not capitalize on that. Okay, so it says awk. So that means it successfully actually created two coroutines. We might as well even print some of them. So move RDI and let's move contexts count and let's just like call to print. So it should print 2. Okay, so this is how many we created. Okay. And I just realized the main execution thread, sort of speak, has to be a coroutine as well. But I mean, it already has its own stack and everything. So we kind of need to either have a separate entry point, which is started as a coroutine, or we have to register the current execution as a coroutine. You know what I'm talking about? Because we have already a thing that is executed with its own stack and stuff like that, but it's not registered in the context and shit like that. It doesn't have its RSP and RBP and RIP stored and stuff like that. Like, it was never properly created, sort of speak. So how could we do that? We could have just like created like main, right, created a main and just maybe jumped there, sort of speak. Or maybe, yeah, so maybe we can have a separate procedure or something like a coroutine init. And let's just take the current execution environment and say, okay, that's one of the coroutines. Right. So that's one of these. So the first thing that we're doing here, that's the first coroutine. So we init and then we just do that. So I think that would be fine. So as soon as you run this, main itself becomes coroutine. Right. So it becomes coroutine. So how can we do that? Obviously, we need to allocate a new coroutine, and the way we're allocating, we need to check the capacity one more time, right? Right, because we're creating a new one. So what I'm thinking is that, what if I just make this entire thing reusable? Because it fails anyway, right? So I can basically put it somewhere down there, right? It's assembly, right? So there's no like a fixed boundaries of the procedures. Procedures are just like a social construct, They don't really exist in assembly. There's only a sequence of instructions, right? So, and yeah, you know, there's no procedures, right? So there's just labels and you jump to labels. Like procedures exist only in your head. It's just a construction, right? So that means I can just put this thing in here, and this kind of becomes a procedure, but it's a procedure that never returns. So that means, yeah, I just jump there. It's sort of an assertion. As soon as you jump there, the program crashes anyway, so it doesn't matter. It's a good one, right? So it's like a sync point for any of the failures or anything. It's just like jump there and just die. So overflow fail. It's a good one. I really like that. So yeah. So here is init overflow fail, and we now need to allocate a new context. Maybe it would be nice to maybe factor it out to a separate procedure, but I'm not really sure. And here is the thing. So the next step in allocating the routine is allocating the stack, but we already have a stack. So, but the stack is rather interesting. So the stack currently contains a return address, right? So again, it grows into the left, right? It grows into the left, and it contains the return address. But we actually want to store this thing without the return address. So we may either set the RSP to -8 or something. We can try to do that. So here we're saving all of that stuff. So let me actually grab this thing. So I'm grabbing this thing. So here's the current stuff, and I need to do RSP, but that RSP has to be... I've got an idea. What if I just pop the return address? Okay. Return address is in Rex now. We pop the return address, so RSP contains the stack as if this function was not called. Right, so we popped the return address, so that means now stack is exactly as this thing was not called. And what's interesting is that, so we can set that RSP in here. RBP, yeah, we didn't modify RBP, we can just set RBP as it was, so which actually means that I don't have to put this thing in here. And the instruction pointer is the return address. So you see, when one of the routines will call yield, that means when we switch the context to this thing, it's going to continue execution from its own init. So by using the return address as the instruction pointer for the current thing, we're going to be continuing execution from here. So this is actually kind of cool. But then we need to, yeah, then we need to return to that address somehow. Well, I mean, we can just jump there. So return is basically jump, but from the stack. So jump Rex and push Rex return are two equivalent instruction sequences, right? So you see, so jump jumps into the address in the operand, returns jumps into the address on the stack, and this is needed because call puts the return address on the stack. So, but we already popped it, so we can just jump there. So that's pretty cool. All right. Did I miss anything? I think that's it, actually. I think that's it. I didn't see anything else. All right, let's try to maybe run that and see if it... Okay, so it didn't crash at least, right? So we didn't try to read something unusual. And so we should also, at the end, as we print, we should do RDI contexts count, right? And just call print. Let's actually take a look at that. All right, so this is how many contexts we have. The main execution thread and two counters. Right, and the main execution thread is going to be basically, I suppose, constantly yielding into the rest of the counters. right? It's going to be constantly yielding into the rest of the counters. Okay, but to do all of that, we need to implement the yield, right? How are we going to be doing the yield? This one. Okay, so when we're doing yield, what we need to do essentially, we have context current, which I suppose initially is set to 0, right? It is set to 0. We may maybe even do something like DQ and explicitly set it to 0, so we don't have to worry about this thing being initialized or not initialized, so it doesn't matter. And essentially what we have to do, we have to save the current execution in the current context and switch to the next one. Async await, no, not really async await, it's a yield, right? It's not async await, it's yield. But we can kind of emulate async await in here, but not really. Actually, we can put all of that stuff into different segments with different permissions, if you think about that. So all of that stuff, for example, these messages, they will never gonna be modified. So we can actually put this into a segment that is readable but not writable. This one can be readable, writable, right? So, and the segment with the code can be only executable. Segment executable. So we can actually put that. So as far as I know, it will make the operating system like set up the permissions for the pages accordingly. Right, so this stuff we can modify that. This is just data. It doesn't need to be writable. And this is code that also doesn't need to be writable. So it's only executable. Does it make the application more safe? Do you think, chat? Did they just make it more safe? Did they just make Rust irrelevant? Just with a few instructions in assembly, Rust is completely irrelevant. Submissive and readable, yeah. Submissive and readable, haha. I wonder if it still works, so let's try to compile. Oh, it still works, look at that. So, yeah. Absolute coding. Okay, so how do we save the execution in here? How do we save the execution? We need to take the context's current. So since we've been using RBX as an index a lot, we might as well do the same thing in here. So move RBX. Okay, so we need to save the current execution. So that means it's going to be kind of similar to this. So we save an RSP, but RSP here is scuffed because it contains the return. We literally have to do the same thing, chat. Believe it or not, we literally can do the same thing. We pop out the return address, fixing up the stack. So now we can safely save the RSP, also save the RBP, and also rags becomes the new RP for the current context. Yeah, that's actually perfect. It's actually perfect. So, and now we can basically go to the next counter. So we can increment RBX, but this motherfucker can overflow. This motherflipper can overflow. Maybe we can use a little bit of a simuvge. It's like pepege, but simuvge. So we can compare CMP RBX to coroutines capacity. And if this thing is greater or equal, move RBX 0. Right, and we also have to update the current. Right, so because it has to wrap around and shit. Yeah, look at that. So now RBX pointing at the next context. And we have to restore that context, actually. We have to restore that context. So we have to do this operation, but in reverse. So we set in the RSP from the new context. We set in the RBP from the new context. And we have to set the instruction pointer. But as far as I know, you can't really set the instruction pointer. But you know what is equivalent of setting the instruction pointer? Jump in there. isn't it? I think it is, right? So jumping is setting the instruction pointer. You setting the instruction pointer, believe it or not. So, and you don't even have to return after that. So, and we yield it, we switch the context. So yeah, that's basically it. So we switch the context. So we save the context for the current thing, and now it is the new one. So that's yield, essentially. Right, so this is save. It's surprising how easy it is to take a snapshot in here. You just pop the return address and everything is the environment. And it kind of makes sense, honestly, right? So because you made a call, so you just need to undo the changes that were made by the call, and there you go, you have an environment without the call, so you just save it as it is, and on top of that you have a return address. It's kind of beautiful in a way. It's kind of beautiful in its simplicity. What the fuck? All right, so let's see if this entire shit compiles. Let's fucking go mine and find the. Motherfucker. How do you use Simuvge? Simuvge. Where is the... There was a Felix something something. Yeah, Felix Clouter. Wait, what? Register or memory? I can't put immediate values in there? Are you serious? Who designed this CPU? Cmove can do intermediate, can it? Cmove E? No, it can't. It can't do that. It's only memory. It's all the freaking memory. Brovsky. Brovsky. I don't fucking know. Fuck you. Fuck you. So. Ah, shit. You think you can stop me? You think you can stop me? Fuck you. You can't stop me. I'm unstoppable. Cheers. Anyways, so yeah, that's how you switch. It's actually surprisingly easy. Is it gonna work? I'm not sure if it's gonna work. Okay, so let's try to run it and see if it's going to... Okay, so here is the... Well, I mean, we didn't do any yield, right? So essentially, coroutine go doesn't run the routine right away. It just registers it in the context table. To actually start executing it, you need to yield in the current thread, so it will switch to that. And then that thing will switch as well. So that means counter itself, yeah, it has to call yield periodically in its loop, right? So it's printing and it's going to be yielding. It's printing and yielding, printing and yielding. So yeah, so let's actually see. Okay, so that means the main thread has to also constantly yield, right? So let's actually call yield only once, right? Let's call yield only once. Maybe we even, yeah, let's actually do that in here. So I call coroutine yield. Created two things, yield, and then I print the amount of context, and then print OK, and then exit with 0. And then it's defaulted, which is quite surprising. Jump into no-no zone, probably. It, for some reason, it couldn't jump back. So, did I fuck up something in here? So, maybe it's something with the need. All right, because you see, yield successfully switched to CMP context. I don't think so. No. Ah, to context count. Oh, I see. Okay, I see. All right, context count. You're right. I was about to go into like a long chain of thoughts, but you found, yeah, okay. All right. So here is the output of the first routine, then the second one, and then we printed how many routines we have in here. So maybe it would make sense to actually print them after the OK, right? So let's actually print them after the OK. Where is the OK? So let's put them in here. Let's put them in here. Yeah. So both of the counter routines managed to execute one iteration, but they didn't finish their iteration. So we literally stopped their execution in the middle of them executing and never continued it. So if we do yield twice, let's just call yield twice, 0, 0, 1, 1, then yield another one, and so on and so forth. So we have to do that 10 times until one of them will finish executing. So I suppose we don't have anything in the stack for them to return. So as soon as they will try to return, they will probably jump to some garbage memory. So some sort of a chaos will ensue as usual. Right, one of the things we can do, we can just do forever. Right, so we'll just call these things forever. Just to see what's gonna happen. Yeah, it's defaulted. Right, so that's understandable. So we can introduce something like, I don't know, coroutine finish, and this thing is supposed to finish the current routine. So for now, let's actually put int3 in here. So do we call int3 anywhere? No, we don't. So as we create a new coroutine, look at that. So we allocated a contains index of the Rax contains the RSP of the new routine. So this one is important in my opinion. Let's now subtract 64 bits from Rax. So Rax contains the RSP of the new routine. And let's move into that thing the address of the coroutine finish. So we're literally pushing the return address to the coroutine finish onto the new stack of the coroutine. So if the coroutine will return, it will actually return into this function. So, and in here we can do something. We can print some sort of a message. Right, so let's actually do something like this. Coroutine finish not implemented. Right. So, and let's put this stuff in here. Coroutine finish is not implemented. 0, 10. Right, so, and we can put this stuff in here. A boom. Is it going to... Okay, so something horrible has happened. Don't know what. Wait, what the fuck? That's bizarre. So if I do go, right, so we just added this thing, subtracted Rax and just move. So that's kind of bizarre. You're right. I should have actually put brackets in here. And it's keyword. That is very cool. But then coroutine finish. There we go. Exited with 69. And it called coroutine finish. So what we have to do now, we have to deallocate this entire thing. But the question is, how do we deallocate them? Right, so allocating is super easy. Deallocating is kind of hard. So this is the moment where I feel like it would be kind of cool if I just had a higher level language already. Right, it would be kind of cool if I just like, yeah. So I started with assembly because I didn't want to introduce too much noise by higher level languages, right? So because like I don't know, they will generate some stuff that modifies the stack, and I don't really know what to expect from the stack. But now assembly kind of stays in my way. I want to go like a layer higher. I want to keep all of these like context saving and stuff like that on a lower level, but then go a level higher. You know what I'm thinking? Can I like extract this entire thing into a separate library and link it with C and maybe call these kind of things from C? That would have been interesting. Yeah. I wonder how difficult would it be. So let's give it a try. So let me see. So I'm gonna create a make file. Right. So this is a main. So let's rename it to something. I don't know, like a proof of concept or whatever. Doesn't matter. Let's see, asm. So fasm pog asm pog. Right. So in here we're gonna have make. What I want to do, I want to have a copy of this thing. So let's actually create coroutine asm. Right, and I want to remove everything that is related to the main executable, right? So I want to only leave the coroutine API, right? So then I can use it as a library from, for example, C or C3, I don't know. So we don't need counter, right? Can we implement all of that shit in a high level language? So that's the real question. So coroutine go, coroutine init, okay, so the yield, finish, main, we don't need main anymore. Fuck all of that. Overflow, we need to keep overflow, it's going to be useful. We're actually using it. So all of that stuff, so too many coroutines, that's understandable. Maybe some sort of error. This one is to do. Right, do we need anything else? Nah. Okay, so, and this is not executable, so we need to create like an object file out of that. So coroutine O, let's compile it like this. So it's going to be fasm, coroutine asm. Let's make that, and we have some sort of illegal. Yeah, I do remember that. So if I remember correctly, so if you're creating the object file, you have to use sections now, right? So this is a section, and it's a text section. This is where you store the code. This one, maybe it doesn't matter. So let's get rid of the sections. So I think you don't have to create them. You can just like, yeah, there you go. And create a pretty huge one, honestly. But anyway, we can maybe do something like a section BSS, I think. Yeah, it actually reduced it. This one is a section data. Yeah, maybe having sections is fine in here. So this is section data. And where is the code is section text. Yeah. Okay. So can I just write like a C program that uses all of these procedures? Coroutine asm. Coroutine. So coroutine go. So it definitely doesn't return anything, but it accepts the pointer to the function, and it's a pointer to the function that also doesn't take anything, right? So this is basically, you know, forward declaration of that function in here. Okay, coroutine underscore init. This one doesn't return anything and doesn't accept anything. That one is easy. Yield is kind of similar if you think about it. It's kind of similar. Finish, I think we should not call finish explicitly. We haven't implemented it yet, but yeah, I think we should not call it explicitly. So I think for the user library, this is the API that they should call, right? So, and now we should be able to create something interesting like counter. And finally, we can implement counter in a proper language, right? So int 0 10 plus plus I. So maybe here we can include stdio io stdio printf d like this. So this is the counter, and here is the entry point. And let's do coroutine init, which makes the current execution thread, you know, coroutine. Then we have to do coroutine go, and we just use counter. Let's create like 2 of them, and indefinitely, let's just yield coroutine yield like this. And by the way, we should also yield on each iteration of the counter too, otherwise it's not going to work properly. I guess that's it. So now if I try to maybe build all of that stuff, main.c, and just link them together. Though honestly, if we're using like GCC and stuff, coroutine asm should have been implemented in GNU assembly, honestly. Should have been implemented in the GNU assembly. So GCC o main.c coroutine o. All right, so let's just try to do that. It didn't like the fact that I didn't have a boolean in here. All right. Ooh. Oh, something with real. Oh shit. Can I? How can I build FASM without relocation? Like, or with relocation? I don't know. It doesn't have anything. Fuck. Yeah, I should have been implemented that in GNU ASM, but it uses AT&T syntax, which I don't fucking know, and it's just like, what was that? So, is there anything? Can I just build F? Well, I mean, maybe we can try that. So FPIE. Nah, it doesn't do shit. I think it means that these things should have been compiled with FPIE. Or maybe fno. Yeah, so let's actually do that. No pick. Raw data cannot be used when... Nah, it doesn't want that. Fuck. I don't want to be rewriting that in GNU ASM. You have to use peak compatible code in a coroutine assembly, relative addressing, etc. All right, so let me see. So how do we do relative addressing here? Okay, so let's actually look at coroutine init. How do I do relative addressing here? So do I, because this is a global variable. RIP based. Okay. So how can I instruct move to do relative addressing? If you reference labels without, it will not be PIC. Need to use layer register address instead of move register address. Okay, this one is interesting. So just a second. I need to copy paste this message that was suggested in the chat. So thank you. Layer register instead of... But what's funny is that we need to do moves. So I suppose... So do we use RBX? Okay, so we already use RBX in here for stuff and everything. We can try to rewrite that. But first I probably wanna experiment with the main POC. So I suppose. Yeah, so all of the main offenders are in here. Maybe I can do it without that, chat. Can I just maybe... Can I just compile it like this? Like C? And just link it separately? It also won't work. Okay, so then main O. Because I remember I already kind of did this kind of stuff in one of my programming languages, actually. Let me see. Just a second. So this one. I apologize in advance. So this was an April Fool's joke, but so this is a programming language that I'm not even joking. The entirety of the programming language is written like that, even the source code. So if you can read Russian, you would have a good laugh at it. I guarantee you. So, I mean, it's hard to believe, but I can actually read the source code in here. So here I'm generating FASM and I'm just like calling FASM. And I remember like implementing so I could link with libc. I remember being able to link with libc. So I would call to LD somewhere. Yeah, here it is. Oh, I would actually specify the dynamic linker. Maybe this is one of the things I have to specify. So here, yeah, okay. So let's give it a try. Where is my stuff in here? So LDO main O coroutine O. All right. Okay. Okay, so it just can't find all of these routines, which is understandable. Okay. So it means I need to make them public. Coroutine. Okay, public. Coroutine go. Will you like it? Okay, so that works. So let's go somewhere here. So this one has to be public as well. And yield now. This is public as well. In the function counter, okay, so, printf. So we need to link with, yeah, if you're starting to use linker like that, you have to link with the C runtime yourself. Can I just do something like this? Oh, and it can, yeah, so as soon as you start using linker, you are on your own and shit. Okay. I remember it was somewhere, okay, what was that? Type file name CRT1 or something. Yeah, this one, right, it's a CRT1, isn't it? So it's a CRT1. Did it work? Wait. Holy shit, it worked. Okay, so it does not execute properly. Fuck you. You can't run it. I know. That actually happens when you don't have a dynamic linker. Do I even have this thing? Yeah, so if it can't find dynamic linker, it just like can't... yeah, I can't do things. So this thing exists, so we have to specify the then. I'm going like a really deep. I should not be doing this kind of shit. I definitely should not be doing this kind of shit, but I went pretty deep rabbit hole. So if I implemented it with GNU-C, I think it would have been way easier for me. All right, so I think the next version of this thing has to be implemented in GNU-C. Holy shit! Let's fucking go! Let's fucking go! Look at that! I have coroutines in C, motherfucker! I have coroutines in C. Implemented in assembly, in a completely fucking different assembly, not even a GNU assembly. Fuck GNU assembly. FASM. FASM is the way to go. Hell yeah! Hell motherfucking yeah. Fuck. Like, how do I now use that in C3? How do I use that in C3? That would be interesting, actually. Yeah, so, because in C3, I think you can't create a separate O file in C3 like this. You can't create a separate O file. So that means we won't be able to, like, use this kind of linker trick. Yeah, don't need libmil. But obviously, like, this one is not finished, honestly. It basically assumes that the execution context is not going to optimize out any local variables into registers. One of the things the set jump does, let's take a look at it, chat. Let's take a look at it. So third party musl, and let's find file with the name setgmp, like so, setgmp x8664. Right, so it saves such registers as R12, R13, R14, and so on and so forth. I think this is the register that are usually used for like local optimized variables. Right, instead of putting them on a stack, it would put them on these things because they are not part of any ABI, right? So they're like usually free to use. Make all coroutines volatile. Maybe I also need to make them volatile. Yeah, that's for sure. Yeah, because this is something libmil would do as well. Right. So I feel like on top of just saving RBP and RSP, we have to do this kind of thing. Right. So we're basically kind of extending the implementation of long jumps. So it's long jumps, but also with a clone of a stack. Yeah. So it's like long jumps on steroids. That's pretty cool. That's pretty cool. So, but we're obviously like running out of time already, streaming for 2 hours. I don't know for how long I can go with this kind of stuff, but that's a pretty good base, right? So this is like a proof of concept that this approach works. Honestly, I don't really know how libmil implements that. So this is basically my take on coroutines. Do we have anyone in the chat who knows how like libmil internally works? I think it works kind of similarly, right? We looked into it very briefly, but I think the only thing I saw in libmil is that it basically implements its own, yeah, it's only this thing, which is basically a set jump. Yeah, so it's their own set jump. But I don't see allocation of the stack. It doesn't really allocate its own stack, so I don't really know what's up with that. Right, so it kind of does that, but I don't see the stack situation. Right, so here we do pretty cool shit where we allocate the stack. Though it does allocate some sort of like an anchoring here, which I suspect could be sort of like the, you know, the space for the stack, right? So it allocates the new stack on the current stack or something like that. So I don't know. I don't know what exactly it does. It looks super complicated. Our implementation is actually super simple. Maybe not super optimal, but it's super simple nonetheless. And I'm actually really proud. So yeah, I think I'm gonna continue working on that and maybe use this kind of approach instead of futures in C3, because this is much easier to reason about, right? Much easier to reason about. And in the future, we can even implement similar sleeping on events, because in C3 Fut, we implemented a thing that, okay, so the current future don't want to execute anything until something is available on that socket. We can implement something like this in here too. Like instead of yield, we can do coroutine sleep, right? So, and provide a socket and say write. So, and it basically yields, and the context switcher will put that coroutine into the bat, into the hash table of things that are sleeping. And then on the next iteration, when something is available on the socket, it will wake it up again and start running again. So while the coroutine is sleeping, it's not going to be switching into that. Right, so we can implement a similar thing as we did in the futures library, but in here. So it's not like, it's not that difficult, right? So it's surprisingly simple. Coroutines, when you're thinking about them on a very low level, on a fundamental level, they are incredibly simple. I think a lot of people are confused about coroutines and find them difficult because they are thinking about them on a higher level, right? From the point of view of a high level language. As soon as you go into assembly and think about the stacks and saving the stacks and registers, it just makes sense. It just makes a lot of sense. So yeah, I guess that's it for today. I'm going to continue developing this thing, and maybe eventually we can embed that into C3 and start using it with WebAssembly implementation and stuff like that. So that was actually pretty cool exploration. So let's take a look at the subs. Let's take a look at the subs. Thank you so much, Tim Martina, for 100 bits. I think I already read that the best way to predict the future is to create it. Thank you, thank you, thank you. All right, that's it for today. Thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you all on the next recreational programming session with a who and Mr. Azos, and I love you all. Mwah.